Hi everyone, in this video I'm going to find first partial derivatives of two functions, and I'll just start on this first one and then there's another one down here. Okay, in this first problem we're going to use the quotient rule, and alright, so I'm going to write df dx, and so what I do is I take the derivative of the numerator and then I multiply that by the denominator. Subtract, I leave the numerator alone and take the derivative of the denominator, and then all of that is over the denominator squared. So by the way, one way to write this is using this mnemonic. It's the quotient rule is low, so the low would be the denominator, d high less high being the numerator to low. I don't really go for that. I mean, it's sort of fun. But the advantage of doing that is actually saying, instead of doing the way I showed in the first line, if I have the denominator derivative numerator, if I write it that way, is that when I put that d in front, it's clear I'm just taking the derivative of the numerator. So the mnemonic is low d high less high d low. Draw a line square below. This is sung to the tune of Minnie the Moocher, so which you can find on the movie The Blues Brothers, sung by Cab Calloway. It's also in a funny episode of Jeeves and Wooster with Hugh Laurie and Stephen Fry. Those are Blues Brothers. You gotta watch that one. And then the whole series, I think it's 4 seasons of Jeeves and Wooster, based on P.G. Wodehouse. So, okay. So, sung to the tune of Minnie the Moocher. How do you spell moocher? All right, anyway. So this gives you x plus y. The derivative of x minus y with respect to x is 1. Minus x minus y. And then you come over here, the derivative of x plus y is 1. And, how am I going to get this wrong is by not using the distributive property correctly. Looks like I don't have nearly enough space for this. So it's going to be 2x over x plus y squared because of cancellation. Oh, what? Totally did that one wrong again. Another mistake. Okay. I did it before, I just wrote down canceling. Okay, then we have that. And then if you have the derivative with respect to y, it's the low, the bottom, the denominator, x plus y. Gotta zoom out a bit. So it's x plus y, the derivative of, it's the derivative of the numerator times the denominator. I'm going to put it low d high. Less the high derivative of the low, d low. I mean, the thing is that I really often write this down using the prime notation, just putting a little thing like that, which is fine, except with partial derivatives, it's not clear whether we mean the derivative with respect to x or y. So that's why I'm not doing that. So, okay. So this is x plus y, and the derivative of x minus y is -1. X minus y, the derivative with respect to y is 1. So apparently this is negative x minus y minus x plus y. And there we have cancellation of those two. And then, of course, I should also write x plus y squared. So that's negative 2x over x plus y squared. Alrighty, that seems to have done that, done the problem there. Let's try this one. Finding these partial derivatives of, you can zoom out a little, just look at that screenshot. Take a screenshot of that. So the same thing, find the first partial derivatives of the function. It's the same directions, let's go down there. So just remember that the derivative of ln u is going to be 1 over u times the derivative of what's inside. D standing for derivative, and say if you're doing with respect to x, you put a little x there if you want. So for this one, but also you can use the, this notation, Leibniz notation. So for logarithms, you take the derivative, you write a fraction and you put the denominator, not the denominator, you put all the input of all this stuff in here, this input function called u, that all goes in the denominator, and then you take the derivative of what's inside. And if you feel like you need to, you could break that into 2 steps. Hey, what if I mix notation, wrote dx? That would be interesting. But I guess I won't do that. Okay, d dx. So working across, that's just going to give 1 over x plus 2y plus 3z. You can sort of see a pattern. That 1 is the coefficient of x here. So you see the d dy of w is going to be the same thing, except now when I do d dy of x plus 2y plus 3z, I derive x with respect to y through 3z with respect to y. Those are all zeros. It's just the derivative of 2y, and that gives 2. So it looks like for this problem, I just look at that coefficient. Anyway. So moving ahead here. So this is the derivative of z, x plus 2y plus 3z, all divided by x plus 2y plus 3z. So we look at that coefficient of z. Oh my goodness. There we are. Show the 9, Nate. Okay, that's it. So just, I don't know, is that very difficult? I would say it's not super neat, my final answer, but partial derivatives, 2 examples. Okay, everybody stay safe out there. Okay, thanks, bye.